In this topic, we're going to look at collisions in one dimension, and specifically, we're going to look at maybe two opposite extremes of that. There are, in reality, kind of in between collisions to these two, but we're going to focus on these two because it turns out they can be analyzed based on some simple formulas. So the first category is totally inelastic collisions, which have the character that the kinetic energy that was there before the collision is lost, or at least lost as much as possible. Maybe a better way of making the statement more correct would be to say that in the center of mass frame, the kinetic energy is actually completely lost. A maybe more everyday language description of this type of a collision is this is when two objects collide and then stick together. That's why, like, if you look at it in center of mass frame really means like looking at it from the perspective of the center of mass point. Well, if you just take any old totally inelastic collision, the center of mass point might actually be moving, and when the objects stick together, there might therefore still be some motion, which means there's still some kinetic energy. But in the center of mass frame, the final state after this collision would be two objects stuck together and at rest. And so in that situation, all the kinetic energy would be lost. The opposite extreme of that are the totally elastic collisions. For those, the kinetic energy is perfectly conserved, 100%. In that sense, maybe totally inelastic collisions are easier to achieve in reality than totally elastic collisions. In reality, there's usually some percentage loss of energy anytime there is a collision, but this condition will allow us to do a mathematical analysis. It leads to some formulas that we can use. The description of this type of a collision is maybe a bouncy collision. So in other words, the objects bounce off of one another. Now, looking at the formulas on the key concept page here, the first formula I have there is a center of mass velocity formula, and it turns out that's exactly the formula you want to use if you want to analyze a totally inelastic collision. Usually the question you have is like, if I take two objects, they collide, they stick together, so it's a totally inelastic collision, what is their velocity going to be after that collision? Well, once they're stuck together, those two objects, basically the center of mass is somewhere like between the two objects, maybe where they're stuck together, or maybe more in one than the other. But in any case, the velocity of the two objects together is exactly equal to the center of mass velocity at this point, because they are no longer moving separately. And so in that sense, the final velocity is the center of mass velocity. But we're going to be able to show that based on momentum conservation, whatever the center of mass velocity was before the collision, that's going to be equal to what it was after the collision, which means that the final velocity really is just equal to that center of mass velocity. So that formula is pretty much all we need, therefore, for dealing with inelastic collision type of situations in one dimension. So this formula again, actually this formula you could use in two dimensions because it's, or more, I guess, because it's written with generalized vector notation. So we could theoretically use it for more than one dimension. This next set of formulas here, this is all kind of part of the same bullet here. These are the formulas for the totally elastic collisions, and these formulas actually only work in one dimension. And these formulas are derived based on the combination of conservation of momentum and the conservation of kinetic energy, because that's basically one of the things that describes what we mean by a totally elastic collision. The one thing I've repeated down here, I think we've seen this in a previous topic, is we got to remember signs, because even working in one dimension where we're not necessarily doing a lot with like different components of vectors, we're just looking at maybe one component, x component perhaps, but if you have, say, a right pointing velocity on one object and a left pointing velocity on another object, you're going to have to distinguish those two with a sign, and maybe conventionally the left pointing velocity would be negative unless you chose to break that convention for some reason, which is okay as long as you do that consistently. Now, the way these two formulas here work, there's some newer kind of like subscript notation here, but basically the idea is V10 is I could also say v1 naught, is the initial velocity of object 1. v2 0 or v2 naught is the initial velocity of object 2. Same thing in the second equation. So basically what these two equations do is you plug in those initial velocities and you get the final velocities after the collision. And part of that, of course, is you need to know the two masses of the two objects that have collided in one dimension.